Hello everyone and welcome. In this video, we're going to continue with our discussion on L'Hopital's rule, and today we're going to take a look at the indeterminate type, infinity minus infinity. So let's suppose you're working on a limit, and the limit has this following form. The limit as x approaches c of f of x minus g of x, where f and g are both going to infinity, or they could also be both going to minus infinity. Then it turns out that this limit may or may not exist, and is called an indeterminate form of type infinity minus infinity. So first, let's convince you of why this is indeterminate. Let c be your favorite real number, and let's consider the limit as x approaches 0 from the right hand side of 1 over x, so this is my f, minus this other function, let's call it g. It's 1 over x minus c. So as you can see, when you approach 0 from the right hand side, this will go to infinity because you're doing 1 divided by a very tiny positive number. It's going to go to infinity. Same reason this is also going to go to infinity. Now we can simplify this. The 1 minus x and 1 minus x cancel, and you're left with the limit of a constant. The limit of a constant is just c. And so this limit evaluates to c. And c could be anything, right? c could be 5, then the limit would evaluate to 5. c could be negative pi, then the limit would evaluate to negative pi. And so I hope this example sort of illustrates to you why this is indeterminate. You cannot be certain about the value of this limit just by looking at the form. You will have to do some more work. In this case, we had to do sort of like simplifications, or we can actually determine the answer. And so that's what it means to be indeterminate form. A limiting value cannot be predicted from the given form. And so you have to change the form so that the answer can be revealed. Now let's talk about what happens if you come across infinity plus infinity. Well, if you come across infinity plus infinity, you have two very big numbers being added together. And so as a result, you're just going to get like an even bigger number. It's not indeterminate. Or if you have minus infinity, then you have two very large and negative numbers being like added together. And as a result, it's going to become even more negative. And so these are determinate forms. They're not indeterminate. When you see something like this, you can just put the answer there as infinity or minus infinity. But when they have opposite sign, like one is plus and one is like minus infinity, or minus infinity and then this is plus infinity, then that leads to this indeterminate form, because there's sort of like a fight going on which one grows faster or which one takes precedence. So we don't know, like the limit may exist, may not exist. It might approach, they might cancel out and approach some finite value. That's why you have to be careful when you have this indeterminate difference. And now let's discuss some approaches on how you can tackle these indeterminate differences. So as we have been discussing, L'Hopital's rule only applies to indeterminate types of 0 over 0 or infinity over infinity. If it's not in this form, then you cannot apply L'Hopital's rule. So to solve this indeterminate form, infinity minus infinity, you have to somehow convert this indeterminate difference into an indeterminate quotient. Now this one is a little bit more tricky than the indeterminate product, but let me give you some tips and some general guidelines of what you want to try to do. So let's say you have this limit as x approaches c of f minus g, and f of x approaches infinity, g of x approaches infinity as the inputs approach this limiting value c. In other words, you have the indeterminate difference. So to convert this indeterminate difference into an indeterminate quotient, here are some common techniques you can do. If you see fractions, then I recommend you combine those fractions into one big fraction. You want to get common denominators and combine into one big fraction. This is going to be your most common technique on how to solve these problems. Another technique I can recommend, if you don't see any fractions showing up or no obvious way of getting a fraction, then try to factor something out. And the other thing I can mention is also you can try rationalizing or multiplying by conjugates. And that is another way to sort of get convert a difference into like a quotient. Okay, so keep these three things in mind. Most often you're going to just use the first technique, but in case you get stuck, try factoring or conjugate. Hopefully that cracks the problem. Okay, so now let's take a look at a few examples. For the first example, we have the limit as x approaches 0 from the right hand side of 1 over x squared minus 1 over tangent x. So as you approach 0 from the right hand side, the first function is going to approach infinity. You're doing 1 divided by a very tiny positive number. And similarly, 1 over tangent. Well, tangent of 0 is going to approach 0. So you're doing 1 divided by a very tiny positive number. This fraction is going to also blow up to infinity. So yes, we do have infinity minus infinity. We have this indeterminate difference. But here it's pretty obvious, like we already have these two fractions. So let's try to get common denominators and combine it into one big fraction. So to get common denominators, I would multiply this one by tangent x, and the other fraction by x squared and x squared. And so that gives me my common denominator as x squared tangent x, which is what I put here. And then the numerator is just going to be tangent minus x squared. Tangent minus x squared is what we put it over here. So now when you try to plug 0 in, what you have is 0 on the bottom, and you also have 0 minus 0 on the top. So yeah, 0 over 0. And there we go. We successfully converted this indeterminate difference into an indeterminate quotient. And the top and bottom are both differentiable, so let's go ahead and apply L'Hopital's rule. Let's differentiate the top. The derivative of tangent is secant squared. The derivative of x squared is just 2x. To differentiate the bottom, we will have to use a product rule. So we differentiate the first function, that gives us 2x. We keep the second function the same. Plus, you keep the first function the same, and you go ahead and differentiate the second. The derivative of tangent is secant squared. Now we check if it's still indeterminate. When you plug in 0, this term will go to 0 because it has an x. This term and this term will both go to 0 because they both have an x. Now what about secant? Well, secant is 1 over cos, right? 1 over cosine of x. And you're plugging in cosine of 0. Well, cosine of 0 is just 1. So this evaluates to 1. 1 squared is just 1. So this is just 1. So 1 divided by a very tiny positive number is going to blow up to positive infinity. And so that's why the answer is positive infinity. Now let's take a look at our next example. Here we have the limit as x approaches 0 of cotangent x minus 1 over x. So as you approach 0, cotangent is just 1 over tangent, right? And tangent will approach 0. 1 over a very tiny positive number, that's going to become very large and positive. So yeah, cotangent is approaching infinity. Similarly, we have 1 divided by a very small number. So this is also going to approach infinity. So we have infinity minus infinity, and that is our indeterminate difference. Now here, it might not be as clear on how to get this into one big fraction, but just keep in mind that cotangent is 1 over tangent. And then you can also replace tangent with sine over cosine. So overall, we get cosine over sine. Right? So cotangent is cosine over sine x. So we do the substitution over here, and now you can see that we do have two fractions. So we get common denominators, and we write as one big fraction. To get common denominators, I would multiply this one by sine x, top and bottom. And for the first fraction, I would multiply by x and multiply by x. So the common denominator is x sine x. And for the numerator, we get x cosine x. Then there's a minus sign here, minus the sine x here. And that is the numerator. Now let's check the type of indeterminate form. When we plug in 0, the bottom is just going to be 0 because of this x term. And then the top is also going to be 0, and this is also 0. 0 minus 0 is 0. So we have 0 over 0. So we have successfully converted the indeterminate difference into an indeterminate quotient. Now let's apply L'Hopital's rule and differentiate the top and bottom separately. To differentiate the top, we will first have to use product rule. We differentiate the first, we just get 1. Leave the second function the same, that's cosine. Then you want to leave the first function the same, x, and then differentiate the second, which is negative sine x. So I brought the minus sign over here. Now the derivative of sine is just cosine, that goes there. And then for the denominator, we again have to use product rule. The derivative of the first is just 1, keep the second one the same, plus keep the first function the same, and differentiate the second, you get cosine x. Now let's try to simplify this a little bit. I see that cosine x and minus cosine x will cancel out, and so I'll get this form. Now when I try plugging 0 in again, I have 0 on the top, and I also have 0 on the bottom. So it's still 0 over 0. As a result, I will apply L'Hopital's rule again. So to differentiate the top, we have to use our product rule. The derivative of minus x is just minus 1. Keep the second function sign the same. Then it's going to be plus the first function. So it's just going to become minus x then. And the derivative of sine is cosine x. Now for the bottom, we have to use the sum rule along with the product rule. The derivative of sine is cosine. And then the derivative of x sine x, we have to use product rule. The derivative of x is just 1. You keep the second function the same. Then you put a plus sign, and you keep the first function the same. And you differentiate the second, which gives you negative sign, and that's why there's a minus sign here. Now let's try to evaluate the limit once again. If you plug in 0, you can see the top is just going to be 0 minus 0. And on the bottom, we actually have 0 here. We have 1 and 1. So we have 1 plus 1 on the bottom. That's 2. So it's no longer indeterminate. It's 0 divided by 2. The answer is just 0. For the next example, we have the limit as x approaches infinity of e to the x minus x. As the inputs increase without bound, the function e to the x and x are both going to approach infinity. And so we have indeterminate form of infinity minus infinity. Now this one is a little bit more tricky because there is no obvious way to convert this into a fraction. So here I would actually try to factor. So in this case, let's go ahead and factor out an x. Then we're going to be left with e to the x over x minus 1. Now as x approaches infinity, well, of course x is going to go to infinity. And we can show using L'Hopital's rule that this also grows to infinity. E to the x, the exponential is dominates. It grows much faster than just a linear function. So we can show that formally by using L'Hopital's rule that this will approach infinity. But once we do that, what we'll have is infinity times infinity. And infinity times infinity, that's not indeterminate, right? As we discussed, that's a determinate product. It's just going to be infinity. You're taking two big numbers and multiplying them, you're going to get an even bigger number. So the answer is just infinity. Now let's also show this limit. Let's show that this limit is actually infinity. To do that, let's go on the side. And what we notice here is that this is an indeterminate quotient. We have infinity over infinity. So L'Hopital rule applies. We differentiate the top and bottom. We get e to the x divided by 1. And now it's no longer indeterminate. As x approaches infinity, e to the x is also going to approach infinity. And here I would like to mention something. You see, we applied L'Hopital's rule, and the limit is not a finite number. But L'Hopital's theorem said that as long as it's plus or minus infinity, the theorem is still valid. And so everything I've done over here is still perfectly valid. Even though the limit doesn't exist, right? Because infinity is not a number. L'Hopital rule still applies when the answer evaluates to plus minus infinity. You can conclude that the original limit is also plus minus infinity. And so there we go. That justifies that we are multiplying two very large quantities, and as a result, the limit evaluates to infinity. Great, so that brings us to the end of today's class, in which we covered indeterminate differences and how L'Hopital rule doesn't apply directly, but there are some techniques you can apply, like trying to combine terms into one big fraction or factoring, so that you can convert that indeterminate difference into an indeterminate quotient and then apply L'Hopital's rule. In the next lesson, we're going to cover indeterminate powers. They are a little bit more involved and complicated than what we're doing here, but they're pretty interesting. So I'll see you then. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.